So we've been working on moles. Last time that we checked in, we worked on moles, mass, particles, converting between. So there's one last little link that we're going to look at, and that's volume. So we're going to start off with our first skill, one-step conversions with volume now. Just kind of throwing that in there. So whenever we talk about volume and moles, we have to kind of acknowledge what's called Avogadros Law. So Avogadro's law, which we'll go more in depth on later in the year when we cover gases, basically states that two gases, when they're equal temperature and pressure, if they have the same volume, they have the same number of moles of the gas. Doesn't matter what gases they are; they can be two completely different things. But if they're at the same temperature, same pressure, and the same volume, they will have the same number of moles. So he concluded that 1 mole of gas will have a volume of 22.4 liters at STP, known as standard temperature and pressure. So STP is basically the condition set. The conditions are that the temperature is going to be 0 degrees centigrade and the pressure is going to be 1 atmosphere or 101.3 kilopascals. Again, this is something that we'll focus on later in the year when we actually use and get into gases. But this term right here, the 1 mole of gas equals to 22.4 liters. That's what we're calling molar volume because it's giving us a volume if I have 1 mole of gas. So this is constant. Unlike the molar mass where that changed with every compound because elements would have different masses and everything, here we're talking about gases. These gases are going to have the same volume if they have the same moles of them. That's basically Avogadro's law. So this is going to be fixed. 1 mole of gas equals to 22.4 liters. And for now, we're going to assume that everything's at STP. Okay, so this is going to hold true for just about everything. So let's take a look here. How many moles of O2, oxygen, are present in 11.2 liters of oxygen? Okay, so our process does not change. Anytime we convert any kind of conversions, we're going to keep the exact same process of multiplying by a want over half fraction. Okay, how many moles of oxygen? So we want moles of O2 are present in 11.2 liters. So we have liters of O2. Okay, so now we need to fill this in with what do we know about liters and moles? Oh, well, we know that 1 mole is equal to 22.4 liters. Doesn't matter what kind of gas. That's Avogadro's law there. Any gases are going to be subject to this molar volume as long as the conditions are at STP, and we're going to always assume for right now that they're at STP. Okay, so 1 mole of gas contains 22.4 liters. So we get 11.2 times 1 divided by 22.4, and basically that's going to be half a mole of oxygen. Nice and easy. So let's move on to another example. How many liters of carbon dioxide are present if I've got 2.25 moles of CO2 gas? Okay, so we got 2.25 moles of CO2 times, well, now we want to know how many liters of CO2 that's going to be, and we have moles of CO2. Okay, so once again, 1 mole is equal to 22.4 liters. This is any gas. Previous example is oxygen. Now we got carbon dioxide. Doesn't matter. Holds true. So we're going to have 22.4 liters for every 1 mole. So we get 2.25 times 22.4 divided by 1. And this is equivalent to 50.4 liters of CO2. Okay, so we're still keeping this the same. Always setting up this fraction. That way our units cancel and we have whatever unit we want at the end here. Okay, that's probably the most important part to remember here, just setting up the fraction the right way. It's really easy to flip the numbers and divide instead of multiplying. That's just why you want to really pay attention to the units. Units matter. Okay, so covering the one-step conversions, let's kind of take it up a notch, and let's go to our second skill here, two-step conversions. Kind of tossing a little bit more into that. What more can we toss in? Well, we can toss in mass. Okay, so this will work with particles too, but usually when we talk about reactions and gases and everything, we're actually more concerned about the mass of it. Now, there's not really a direct conversion between mass and volume unless we're talking about density. Okay, density does give us that link, but for right now, we're going to look at other ways here. So we're going to work with the mole, which is why we're not going to really incorporate density here. We just want to try to emphasize this mole. So I want to know how many grams of steam, which is basically water, are present if I have 2 liters. So imagine I've got like a 2-liter bottle of soda, that's all water. I want to know how many grams of water are actually in there. Okay, so I've got 2 liters of H2O, okay, because steam is just water. So we're going to look for moles here because moles is always going to be our median. Whenever we're doing 2 units together and they're not, and one of them is not moles, we're probably going to need mole anyway because moles have to always be involved with everything. So 2 liters of water times, well, now we want moles of water, and I have liters. Okay, so it's steam, water's in gas phase. Great, which is perfect. How convenient, because now 1 mole of water is equivalent to 22.4 liters of that. Okay, so 2 liters times 1 divided by 22.4. In 2 liters of steam, I have 0.089. Sorry, I'm just cleaning up that 8 a little bit. So 0.089 moles of water. Awesome. So now it's got one more step. We have moles, got to go to grams. Okay, so 0.089 moles of water times, well, now we want grams of water. I have moles, grams and moles. Oh yeah, that's molar mass. Okay, water has a molar mass of 18.02 grams per mole. So it's 18.02 grams for every 1 mole. So our 0.089 moles times 18.02 divided by 1 means that we have 1.608 grams of water. So filling up a 2-liter bottle of soda with only water is barely 1.5 grams of water. Go figure. Well, that's basically how you do this here. Again, moles is that middle section. Moles is going to be involved with everything. And this is mainly just kind of getting used to saying that molar volume is constant. 1 mole is 22.4 liters. Really, the only thing that's going to vary is going to be the molar mass. That you have to adjust for every compound because the masses of all the elements will differ. Everything else basically remains the same.